Hey guys, and welcome to the rest of our Chapter 4 lecture for this stats class. So, we're going to first start about talking about a couple other special things of probabilities to special situations, and then from there we're going to move on to talking about how to count. Now, this is more complicated than just simply, using your fingers and toes, and so we're going to go in through 5 different ways of counting. But first, let's talk about some more probabilities. So we're going to expand a little bit on conditional probability, and we're also going to talk about how we can find the probability of at least one of something happening using the multiplication principle. This idea of at least one is a really kind of crucial idea in this concept and the way we're going to think about it, and it will actually help us when we look at counting later. So we're talking about the probability of at least one. So let's say we have 10 things chosen, and we want to know what's the probability that at least one of them has the condition we're looking for. That's a lot, because that means we have to look for what's the probability that one of them does, that two of them, that three of them, four of them, five, all the way up to 10, and then we have to add those all together. What's easier than that is to find the probability of the complement, or the opposite. So if we're looking for the probability of at least one, we can simply look for the probability that none happen. And so that's this idea of kind of using those complements to really help you out, looking at the easier situation. It's a lot easier to find the probability that nothing happens than the probability that at least one thing happens. And so this is just kind of giving us kind of that formal definition. If A is getting at least one event of some event, and then A complement is getting none. So to find the probability of a complement, okay, we are finding the probability that A doesn't occur. And once we have that, we can use those complement rules that the probability of A plus the probability of A complement is equal to 1, and all of those different rearrangements. And in this case, what we're going to use is that the probability of A is equal to 1 minus the probability of A complement. So we're going to go through a little example here. So in a study by SquareTrade, they found that 6% of damaged iPads were damaged from bags or backpacks. In other words, being shoved in there and banged around. So if we have 20 damaged iPads, we want to know what's the probability that at least one was damaged from a bag or backpack. Now that's a lot, right? We talk about with 10, right? We have to find 1, 2, 3, all the way up to 10. With 20, we have to find all the individual probabilities that exactly 1 is damaged, then exactly 2, then exactly 3, then exactly 4, and so forth. And that's a really kind of daunting calculation, and it's actually more daunting than you even think about. But what's far simpler than that is what's probably that none of them are damaged by being in a backpack. And so let's look at this. Okay. So this is just kind of going through what I just said. So step 1A is at least one of them. Then the complement is getting none, all 20. So to find the probability of the complement, to find the probability that there are no damaged backpacks, we can simply use the multiplication rule, right? So we are looking at 6% damaged by bags. So for it to not be damaged by a bag, that probability is 0.94. Okay. So that means the probability that iPad 1 is not damaged by a backpack is 0.94. Then we multiply that by the probability that item 2 is not damaged by a backpack, item 3, all the way up to item 20. And so what we end up with is 0.94 raised to the 20th power, which gives us 0.290. So that means the probability that none of these 20 backpacks are damaged by a bag, none of these 20 iPads are damaged by a bag or a backpack is 0.290, which means the probability that at least one of them is damaged by a backpack is simply 1 minus that, or 0.710. So we can then take that result and we can interpret that. We can say that for a group of 20 damaged iPads, there's a 0.710 probability of getting at least one damaged iPad that was damaged in a bag or a backpack. Okay. So we can see that the probability is not very high, so it's reasonably sure of getting at least one. We want to get more than 20 iPads. So if you're trying to find at least one iPad that was damaged by a bag or a backpack, you might want to get more than 20. So that's how we can use the complement rule and this idea for at least one. And it actually can expand further than that as we get more kind of more comfortable with counting and some of the things we're going to be doing and some of these other probability methods. If I said what's the probability of getting at least 2 of 20, that's still a very large calculation. It's a much simpler calculation to do none or 1. And so we can still use this idea of finding complements to help us out. If we know the whole thing, which with probabilities, the whole thing is always 1, if we find the complement, we can just take that difference. So now I want to talk about conditional probability. We already talked about conditional probability when we talked about the multiplication rule, right? We talked about if two events are not independent, right? We have the probability of A times the probability of B given A. And what that means is that's the idea that we need to find, we're looking at the probability of event B happening given that A has already happened. And in the examples we were dealing with there, we were talking about things like drawing 2 cards without replacement. So the second card, there was no longer 52 cards in the deck. There's only 51 because we already took 1 card out. However, we can actually do conditional probability on a single trial, on a single event. So we're going to talk about that here and kind of the formula that we can use to do that. So this is the notation that we already talked about, right? Probability of B bar A, which we just say probability of B given A is the way we read that. And so what we're doing is we're assuming that A has happened, and now we need to find the probability that B has also happened, or B will occur. And the way we do that is we use this simple formula. So the probability of B given A is equal to the probability that A and B happen divided by the probability of A. Now, we may think that, well, probability of A and B is exactly the kind of multiplication rule, and we need that to do this. But there's situations, and we're going to see in this example, where we know the probability of A and B, but we don't necessarily know the probability of B given A, and that's what we're using to find here. So we're looking at this example here. We've got 2 parts, A and B, and they're going to basically just flip our event A and our event B. So if one of 555 subjects is randomly selected, find the probability that the subject had a positive test result given that the subject actually uses drugs. So this is looking at a drug test, say something you would take to be employed at some companies and stuff like that. And there's something called a false positive and also false negatives. And what those are simply referring to is somebody who tests positive but actually doesn't use drugs, or somebody who tests negative but actually does use drugs. And so those are kind of issues and stuff like that with tests that we have to minimize when the test is being created, but that's not this class. That's something totally different. So that was part A. Part B is still just one person, but we want to find what's the probability that the subject uses drugs given they had a positive test result. Okay. So there's an intuitive way to think about this. So for part A, we want a positive test result given the subject uses drugs. So if we come back to this table, okay, we can look. So we are told, we are assuming the person uses drugs, right? That is our condition, right? Given the subject uses drugs. So that means we are in this group here. So the subject uses drugs is what we have already met. So there's 45 and 5. So there's a total of 50 people or test subjects that already use drugs, that are using drugs. We want to know what's the probability that of them we get a positive result. Well, of those, 45 had a positive result. So intuitively, we can just take this idea and we can get 45 over 50, or 0.9 probability. Now, if we use this formal formula, that probability of B given A is equal to the probability of B and A divided by the probability of A. So we can use this to find that exact same thing. So the probability that a subject uses drugs and had a positive test result, okay, if we look back at that table, 45 over 555. So there are 45 subjects that had a positive test result and they used drugs. And there's 555 total. So that was really simple, right? Finding that kind of intersection is really nice and easy. Now, the subject that used drugs, that's 50. out of 555 because the used drugs, there's 45 that test positive, 5 that test negative. There's 50 total. And so using this formula, we get 45 divided by 550 divided by the fraction 50 divided by 550. And when you divide a fraction by a fraction, some of you may remember that's multiplying by the reciprocal. So this would be the same if you wanted to do this by hand. I mean, most of us are just going to grab a calculator, and that's fine. But doing this by hand, then we'd get 45 over 555 times 555 over 50. Now, the two 555s are going to cancel each other out, and we're left with 45 over 50, which is just what we had from the intuitive way. Okay. Now, depending on what information you're given, so this table is pretty easy to use. The intuitive approach is pretty easy. Okay. So keep that in mind when you're doing these things. Now let's look at the other case. We want to find the probability that the subject uses drugs given a positive test result. Okay. So we're assuming that we have a positive test result. Now, if you go back to the table, either skip through the video or hopefully you wrote the table down, there were 70 different subjects that had a positive test result. So what we want to do from there is we want to see, okay, how many of them actually used drugs? Well, there's 45 that used drugs and had a positive test result. So we get 45 over 70. Okay. So the first result, okay, gives us a probability that somebody tested positive given that they used drugs is 0.9. The second result is the probability that somebody uses drugs given they had a positive test is only 0.643. Now, notice that's a significant difference. All right, so what those two things are saying, this first thing is saying that if you use drugs, you're going to have a positive test result 0.9 with a probability of 0.9 or 90% of the time. Okay. But what the second one is saying is this is saying that if you have a positive test result, if we're going to say the employer and we have somebody who has a positive test result, that means the probability that they use drugs is only 0.643. So just because they have a positive test result doesn't automatically mean they are using drugs. So kind of interesting, right? One thing that's really important to look here is these are not equivalent. So the probability of B given A is not the same as the probability of A given B. Now, there are some rare cases where it may be equal, but it is not always true. Oh, bless you. So now let's move on to counting. You may be thinking like, woo, counting, yay, I can do that. But what we're talking about is counting complex situations with lots of things going on and kind of some challenging thought processes. Counting problems are one of the really fun things in mathematics because they really involve critical thinking. And one thing that is really big with them is they are a really unique problem set in that you can talk to some of the most brilliant mathematicians, give them a medium level counting problem, and they're going to struggle with it. It requires a different way of thinking sometimes, and that's what we're going to try and build up, some different knowledge on counting. So these 5 formulas that we're going to go through are not the be-all end-all for counting every single possible thing, but they do give us a really strong foundation, a really good base for counting the majority of things, and it's going to be sufficient for this class. So those 5 counting methods are, we're going to use the multiplication counting rule, which is sometimes referred to as the fundamental rule of counting. We're going to use the factorial rule. We're going to have permutation with distinct items. We're going to have permutation with non-distinct items. And we're going to have combinations. Okay. There's lots of conditions going on for all of these different things. And as we get to them, we're going to kind of describe them and break those up and verbally I'll tell you about them. So the multiplication rule is really the kind of foundational thing. It's the base thing that everything else is built off of. And what the multiplication rule does is it basically says if there's and we're going to use these subscripts N1, N2, N3. If there's N1 ways for the first event to happen, and N2 ways for the second event to happen, and N3 ways for the third event to happen, and that can go on for however many long, then the total number of outcomes, we just simply multiply them. It's really simple. So a really common example of this is a 4-digit passcode. So if you think about your standard PIN code for your ATM card or things like that, you have the option of the digits 0 through 9. So what that means is you can use 10 possible values. Now, if you count, including 0, we get 10 possible values. So that means for the first number, if there's no other restrictions, so you could have the password of 0000 or something like 1234, then our first digit has 10 possible ways it can be chosen. Our second digit has 10 more possible ways. Our third has 10 more possible ways, and our fourth has 10 more. And so, sorry, gonna maybe sneeze? No? Oh, springtime is great for allergies, whether I'm doing a video or not. So each of the 4 possible characters of your PIN code, each one has 10 possible choices. Now, these choices are all independent of each other. There's no influence. There's no, if I choose this, I can't choose it later, anything like that. And so because of that, we can use this multiplication rule and simply do 10 times 10 times 10 times 10. And so for a standard 4-digit PIN, there are 10,000 possible combinations. And so that means the probability that somebody randomly guesses the same PIN as you, or if you wanted to, randomly has the same PIN that you have one unique PIN. So when we're talking about probabilities like this, we're really going to the classical approach, right? If you remember back from last class, that means we're looking at the number of ways it can happen over the number of ways anything can happen, right? Or the number of total simple events. So if we want to know the probability that somebody randomly guesses your PIN code for a 4-digit PIN, well, there's only one way they can guess that correctly, and that is your exact PIN. And so that means there's only one way it can happen. But as we just found out, there are 10,000 different ways that these PIN codes can be ordered, which means the probability that somebody correctly guesses your passcode is 0.0001. And that's how we can use this counting rule as well as probabilities and create some nice fun problems. Let's move on to number 2, the factorial rule. Okay. What this is a situation where the order matters. Okay, so we're talking about an arrangement of things. So when we say an arrangement, right, that means different to come in first, to be first than it is to be second, than it is to be third. So ABC is different than CAB, just different than BCA. So if we have n different items and all n of them are selected, okay, so what that means is we have some set of things and we want to arrange all of them in a line. How many different ways are there to do that? And that is simply n factorial. That's how we read this. This n exclamation mark, we read it as n factorial. And what does that factorial symbol do? Very simply put, it is taking a positive whole number and multiplying it by every positive number below it, positive whole number below it in a decreasing fashion. So say 4 factorial would be 4 times 3 times 2 times 1. And by a special definition, because we have to have this, otherwise a lot of things in mathematics and specifically probability fall apart, 0 factorial is 1. That's a nice, fun, and unique weird thing. So the factorial rule is really nice and easy to use. It's really based on the idea of the multiplication rule. And what it really simply is that every spot you choose, so if you have, say, 10 people for that first spot, there's 10 choices. But now you've put somebody in that first place. So now there's no longer 10 choices, but now there's 9 choices. And so the second event has only 9 options. Now the third event, you've used up 2 people, so there's no longer 10, but now there's 8 people. So you get the first event has 10, the second has 9, the third has 8, and so forth going on down, and we end up with 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which is 10 factorial. Okay. So let's look at an example. So if a statistics researcher must personally visit the presidents of the Gallup, Nielsen, Harris, Pew, and Zogby polling companies, how many different ways can they make their travel? Or how many different travel itineraries are possible? And if you randomly select an itinerary, what's the probability that the presidents are visited in order from youngest to oldest? Now, before we get to part B, I want to think about that. Youngest to oldest. How many ways are there to do that? Well, there's only one, right? There's only one order of them from youngest to oldest. So that means this is going to be a 1 divided by some number type of case again. So since there's 5 different groups, right? Gallup, Nielsen, Harris, Pew, Zogby. Let's go with Zogby. That means to figure that out, it's simply 5 factorial. So there's 5 choices that we go see first. But now we've already seen one of them, so that to see second, there's only 4 choices. To see third, there's only 3. To see second, fourth, there's only 2. And last, there's only 1 left. And so we get 5 times 4 times 3 times 2 times 1, which is 120. Now, we do not have to do this manually out like that every time because that is really terrible. What I want you to do right now is I want you to go and grab your calculator. Okay? Grab your calculator and have it with you. And we are going to work on this. Now, I'm using a TI-84. If you have an 83, it's the exact same. It's no different. The only difference is if you had something other than a TI calculator or a non-83, 84, not graphing calculator. If you have like TI Nspire or something like that, things are a little different. You might just have to Google factorial on your calculator. But it's really easy. So if we want to do 5 factorial on our calculator, the first thing you need to do is turn it on, obviously. And then you're just going to hit number 5. Okay? So on your screen, you should see 5. Then you're going to go to math. So that is just below the second and alpha button. You'll see a button that says math on it. Now, when you hit that at the very top of your screen, so you've got a list of things going horizontally across the top, and then you've got a list of things going vertically down. When you first hit math, the list on the top, you should be on the square should be on math, and then you should have like fraction, decimal, cubed, cube root, x root, things like that. What we want to do is we want to press our left or right buttons to get to where we have the PRB highlighted on the top. That's probability. This is a menu we are going to use a lot. Now, if you look down, the fourth option, I believe it should be on both 84s and 83s, is an exclamation point or factorial. So if you just choose that option, so now on your home screen, it should kick you back there. You should have 5 factorial, 5 exclamation points. If you hit enter, you get 120. And that works for anything. So if you want to do something like 24 factorial, okay, you can do that. Now your calculator starts to get a little wonky because factorials grow very quickly. Not as quickly as exponentials, but they grow very quickly. And so even 24 factorial, we get this 6.204484017 E23. So what that means, that E23 is scientific notation. Meaning we need to move that decimal place 23 places to the right. So let's see here. Trying to figure out what the last one. So 13 is the last time. 13 factorial is the last number that will fit the entire digit in there, the entire answer in there. 14 factorial jumps to that scientific notation. So very quickly, it gets too big for your screen to handle. So when we're doing calculations, you can actually end up overflowing your calculator. Basically, there's so many numbers that it has to remember, it can't do it, and it will give you this error overflow. And that's why if we're using factorial and we're trying to do calculations, you don't want to do a bunch of individual factorial calculations. You want to do it all at once so things cancel where they can. And you'll see how that works and where that's going to come from in later counting rules. So since there's 120 possible ways to visit these 5 presidents, there's only one way to visit them from youngest to oldest. So that means that it has a probability of 1/120th. All right. Now, before we get into our third counting rule, we want to talk about the difference between a permutation and a combination. Okay. The big question you have to ask yourself is, does order count? Okay. Does it matter? Is it different to be first, second, and third? Or is it all this, or is it just kind of all a grouping? Okay. So in a permutation, okay, this is an arrangement of items in which different sequences are counted separately. In other words, it matters if you're first, second, or third. Okay, think of this like finishing a race, right? It's different if you get first than it is if you get second. Okay, so a combination is an arrangement where different sequences are not counted the same. So in other words, it's just a grouping. So using the idea of like kind of forming a committee, just a group of people. There's no hierarchy or anything like that. You get this. So in a combination, order does not matter. Okay. So if the order doesn't matter which you choose these things, you are doing a combination. There's a nice little mnemonic that some people use. Permutations, positions, right? It matters what position you finish in or what position you have. Combinations, committee, right? So a committee is typically just considered a group of people. And so permutation, position, combination, committee. That's a nice kind of way that you can kind of help remember that if that works for you. Now, let's talk about the permutation rule. There's a couple things to talk about here, and there's some symbology, and some of them is the actual kind of stuff. So if we have n different items, that's a big thing right there, and different items, they're all different, okay? And we want to choose R of them without replacement, so we aren't picking one and putting it back, okay? If we want to choose R of them without replacement, then the number of permutations is given by this formula. Now, the left-hand side of that equation is we have that little subscript n, capital P, subscript R. The way we read that is we just say NPR. So we'd say like 5P3. Okay. Now notice we have n items and we're choosing R of them. So that means n is always at least as big as R, if not bigger. Okay. In other words, R is less than or equal to n. So in that denominator, we'll never end up with a negative number. Okay. So this formula is n factorial divided by n minus r factorial. Okay. And if you look at your calculator, okay, go back to the math, go over the probability button, just where we're same place we were selecting the factorial. You'll see that second option there is an NPR. Okay. So we're going to talk about how to use that feature in just a second when we do our example. So if you are on your calculator, hit second and mode right next to it, or to quit, and go back to your home screen. So let's look at an example. So in a horse race, a trifecta bet is won by correctly selecting the horses that finish first, second, and third. You have to not only get the correct horses, but the correct order. So in the 140th running of the Kentucky Derby, there were 19 different horses. How many different trifecta bets are there? And what's the probability of getting it correct if you randomly select the finishing? Okay. So what we have, we go back here, we have 19 different horses, and we need to order 3 of them. We need to put 3 of them in order. So this tells us that because order matters, we're doing a permutation. We're not replacing it, so it's not like a horse can finish first and second and third. So if that were the case, we would use the multiplication rule. Okay. If we were selecting all of the horses, that would be the factorial rule. But since we're selecting a subset or a smaller set of the horses, we use the permutation rule. So let's do this on our calculator before we get to the example. Let's see if we can do this. So we have 19 horses total. We need to get 3 of them. So to use our calculator, use that NPR button on our calculator. The first thing you need to do is type in your n. So you need to type 19. Once you've typed 19, you go to math, go over to the probability, and then you need to choose NPR. And now you enter the R value. So in this case, 3. So we want 3 different choices from there. And from that, we get 5,814. If you're getting something different, email me and we'll talk about it. We'll see if we can't get you set up correctly. Okay. And look at that, 5,814. Now, this formula is great, this 19 factorial over 19 minus 3 factorial. And that's something that, if you want to do this by hand, you can, but we're not going to. I'm never going to ask you. I'm never going to force you to do it by hand. We have a calculator for a reason. We live in the 21st century, although it may feel like we don't right now because we're all trapped at home, but so we're going to use that to help us. So the number of ways we can correctly guess the three that finish is one, because there's only one way for the first three horses to finish, which means the probability of randomly selecting this is 1 in 5,814. So what's kind of fun is they show that a winning $2 trifecta bet won $3,424.60. So because of that, it's not a beneficial thing to just guess all 5,814 bets and just make all those bets and you'll win, guaranteed, but you would actually end up losing. So if we did that, so take 5,814 times 2, that gives us $11,628 to place a $2 bet on every single outcome. Now the winnings, so we'll subtract that from the 11,628 that we bet, were 3424.6. So if we made a $2 trifecta bet on all possible outcomes of this 19-horse race, it would have cost us, because including the winnings we would have made, we would have lost $8,203.40. So that's why things like just bet them all isn't actually a worthwhile strategy. Now, the permutation rule with some items identical to others, in other words, non-distinct items. This is a very unique thing. There isn't a nice button for it on our calculator. This is the time we will need to use that factorial rule and to do a big calculation in our calculator. We can simplify things beforehand if we do it on paper, but we can also just hand it to our calculator and have it do it all. The catch is we need to do all of it at one time in our calculator. We don't want to do a bunch of different things, kind of little things at a time. And so what this is this is simply when we are doing a permutation of n items and we are selecting all n items. Okay, so that's a big thing. If you're only selecting a subset and they're not distinct, it gets into a whole other ballgame that we're not going to deal with. So we have n items. They're not all distinct. They're not all the same. Or they're not all different. And we want to choose all of them without replacement. The way we do that is this formula. Now, that piece we're dividing by, that n1, n2, up to nk, those are simply the number of items that are the same as each other. In other words, if we had 5 items that were all the same, then one of those n's would be a 5. Okay? And we'll do some examples and stuff like that to kind of make that a little clearer. I don't really like this example. You guys can read through it and go through. It's not too crazy. But what I want to do is I want to talk about making mathematical words. Okay? So, in mathematics or statistics in particular, probability, a word is simply just any arrangement of letters. Now, that doesn't mean it has to be an English word or any other language word. It just has to be just an arrangement of letters. So, B, 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 B. That is a mathematical word. Now, if we look at, say, the word book, and we want to say, okay, how many different words can be made from the letters in the word book? Because the order matters, right? B-O-O-K is different than B-O-K-O, right? Book and Baco is not the same thing, right? If you said, man, I read the greatest Baco the other day, no one would know what you're talking about. So, order matters here. We're choosing all of our items, but the problem is not all the items are distinct. And so what we do here is it's really simple with book is there are 4 total letters. So that means our n in the numerator here is a 4. Now, one way to think about this is you could kind of go with every different type of thing, every different type of item in there, how many times it occurs for these numbers down here. So in other words, there's 1b, so this would be a 1 factorial. There's 1k, so you'd have 1 factorial again. But another simpler way is just if an item is repeated, it's duplicated. In this case, we have 2 O's. you would have that count here. So since we have two O's, we would have 4 factorial divided by 2 factorial. And that right there gives us all possible ways to rearrange the letters in book. And what does that equal? 4 factorial divided by 2 factorial. Gives us a lovely little 12. So there are 12 different arrangements of B, O, O, and K. So obviously that's one, right? Now, if you flip the two O's, you still have B, O, O, K. And so that's not a different arrangement. And that's what's happening with that division. By dividing by 2 factorial, what we're doing is we're dividing by the number of ways I can rearrange those same items. Now, if you get more complicated words like, say, Mississippi, right? You're divided by a lot of different things, okay? But let's just say I have the letters A, B, and C, but I have 3 A's, 2 B's, and a C and 1 C. Okay, that means I have 6 total items. So I would do 6 factorial. I have 3 A's, so I would divide that by 3 factorial. I have 2 B's, so I would also have a 2 factorial in the denominator. So I would have 6 factorial in the numerator. And then in the denominator, I have 3 factorial times 2 factorial. Since I only have 1 C, I don't need the 1 factorial because that's just 1 anyway, mathematically speaking. And that would give us the number of ways to rearrange, 3 A's, 2 B's, and 1 C. Okay. So that is permutations with non-distinct items. The thing here is we have to be selecting all of our items. Okay. Now, last thing, combinations. So what we're doing here, this is very similar to rule number 3, the permutation of distinct items. The only difference between these two is that with rule 3, order mattered. It mattered what order we arranged the items in. With rule 5, it does not matter the order. And a way to think about that is if you say, oh, we're going to choose five numbers randomly from a hat, we're just going to arrange them from smallest to greatest. So it doesn't matter if I choose 5 and then 2, they're going to be listed out 2, then 5. So it doesn't matter what order I choose them, they're just kind of listed out in a group. Okay. And for this, we use this NCR. And the way we do it in our calculator is exactly the same as the NPR. So we put the number of items we have first, then we go to math, over to probability, and I believe it should be option number 3 is the NCR. Choose that, and then choose how many items you're choosing. Okay. So in California's Fantasy 5 lottery game, winning the jackpot requires that you select 5 different numbers from 1 to 39, and the same 5 numbers must be drawn in the lottery. The winning numbers can be drawn in any order, so order doesn't make a difference. Now, if you've read the post for the forum for week 5, this should be raising red flags that you should be paying attention really good right now. So, how many different lottery tickets are possible, and find the probability of winning the jackpot. So the winning the jackpot would have all 5 numbers, right? So there's only one way to have that happen. So this is just like many of the other ones we've done in these examples. It's just 1 divided by the number of ways it can happen. So since we have 1 to 39, that gives us 39 total numbers, okay? And we need to choose 5. So we're just going to use our calculators to do this. We're just going to do, we have 39 things. So we type 39, go to math, over to probability, and choose that NCR. So right now on your screen should say something like 39 NCR, and then we want to choose 5. We hit enter, and we get 575,757. Okay. So there are that many different ways to choose 5 items from 39 items. Now, the probability that we win is simply 1 over 575,757. It's easy. Okay. Now, what's really cool with these counting rules is that we can combine them in the sense that, especially in the first rule. So when we look at that first rule, we look at, okay, there's N1 ways to do event 1, and 2 ways to do event 2, and 3 ways to do event 3, and we just multiply them all together. Sometimes those are really simple, like how many ways can you choose pizza crust, pizza sauce, pizza topping combination, right? If you've got like thin crust, hand tossed pan, red sauce, Alfredo sauce, barbecue sauce, cheese, pepperoni, chicken. Okay. Those are just three, three, and three. You just multiply them together. Bam, you get your pizza combinations. But sometimes those events have more complicated calculations. And so sometimes to find the number of ways you can do event one, you actually need to use one of these other counting rules. And then once you found that, you need to find the number of ways to do event two. And once you found that, you can multiply those two things together. So keep that in mind when we're talking about this lovely little posting we have for this week. All right, you guys, that is it for this lesson. That's talking about counting. So make sure you guys take your time, really understand these counting rules. I guarantee you this is going to show up on your test. Okay. Get through this homework and study for your test. Remember, Wednesday at 11:30, we'll be doing a virtual office hour review session. Hopefully you guys can make it. I'll see you then.